Hello students, today we see again examples on relations. So let us see first example. Let R be a relation on set A, then prove that R is antisymmetric if and only if R intersection R inverse is subset of identity relation IA. So here we have to prove that if R is antisymmetric, then R intersection R inverse is subset of IA, and conversely, if R is intersection R inverse is subset of IA, then we have to prove that R is antisymmetric. So consider R is relation on set A and R is antisymmetric. So we have to show that R intersection R inverse is subset of IA. So for that, consider pair XY belongs to R intersection R inverse. Now this implies that since this here is intersection of R and R inverse, we can say that XY belongs to R and XY belongs to R inverse. So XY belongs to R and XY belongs to R inverse, that means YX belongs to R. So this XY belongs to R and this YX belongs to R. This shows that R is, now since R is antisymmetric, we can say that if xy belongs to R and yx belongs to R, implies that x is equal to y. If x is equal to y, that means pair xy belongs to identity relation IA, because xx belongs to IA, yy belongs to IA. So x is equal to y means xy belongs to relation IA. Thus, xy belongs to this R intersection R inverse implies that xy belongs to IA. Therefore, R intersection R inverse is subset of IA. Now conversely, let us take that R intersection R inverse set is relation is subset of identity relation IA. Now we have to prove that R is antisymmetric. So for that, let xy belongs to R and yx belongs to R. So if xy belongs to R and yx belongs to R, this implies that this xy belongs to R and here yx belongs to R means xy belongs to R inverse. So xy belongs to R and xy belongs to R inverse. Therefore, xy belongs to R intersection R inverse. Therefore, this implies that xy belongs to IA because R intersection R inverse is subset of IA. Therefore, xy belongs to IA. If xy belongs to IA, then x must be equal to y. So, we have shown that xy belongs to R and yx belongs to R implies that x is equal to y. Therefore, R is antisymmetric relation. Thus, this relation R is antisymmetric if and only if R intersection R inverse is subset of IA. Let us see next example. Let R be a relation on set A, then prove that R is transitive if and only if composite relation of R and R is subset of R, or R circle R is subset of R. So here also we have to prove that If R is transitive, then prove that R circle R is subset of R. And conversely, if R circle R is subset of R, then we have to prove that R is transitive. So first let us take R as a transitive relation. So for R circle R is subset of R, take a pair from R circle R. So let xz belongs to R circle R. So here is composite relation of R and R. Therefore, if there is a composite relation R circle S, then if xz belongs to R circle S, we say that there exists element y belongs to set. If relation is from A to B and B to C, then we say that there is a element y in set B. So here the set A and B are equal, that is R. Therefore, we say that there exists element y belongs to same set A such that this x and y belongs to this R, and y and z, pair yz, belongs to relation R. So there exists y such that xy belongs to R and yz belongs to R. Therefore, R is transitive. Since xy belongs to R, yz belongs to R, this implies that xz belongs to R because R is transitive. Therefore, we have taken that xz belongs to R circle R, and this implies that xz belongs to R. Therefore, R circle R is subset of R. Now conversely, let R circle R is subset of R. Now to prove that R is transitive, let xy belongs to R and yz belongs to R. Now if xy belongs to R and yz belongs to R, since this implies that xz belongs to composite relation R circle R. This implies that since R circle R is subset of R, xz belongs to R. Thus, we have shown that xy belongs to R and yz belongs to R implies that xz belongs to R. That means R is transitive. Thus, R is transitive if and only if R circle R is subset of R. So, we stop here.